Welcome to Digital Education. So today's topic is set theory. In this set theory, we are going to see the definition of set, its properties, how to write down that set, how to represent it, and then we will see different types and the Venn diagram representation. So before moving to the topic, I would like to request you, if you like this video, please like, comment and subscribe to the channel. So let's move. So here in this set theory, so we can say that a set is a group of well-defined objects. So group of objects means it can be a group of students, like people in the classroom, or it can be the different classes offered by a department, like this IT 101, IT 202. It can be the colors in a rainbow, it can be the combination of that one, or it can be the states of the matter, places in the country, or it can be the combination of different elements also, non-related elements like numbers, characters, places. It can be the group of that type of objects also. Suppose if I am having a number representation, it can contain anything. Okay, we can use any set of numbers. So suppose if I am saying that all positive numbers less than equal to 5, so that can be represented as 1 2 3 4 5. This is a set of 1 2 3 4 5. And if I'm saying that it's a set of real numbers, then that set of real numbers can be represented like this. So it is a set of some real numbers, few selected real numbers. Now, how to represent that particular set? While representing, we need to make sure that a set, for that particular set, so order does not matter. So if I'm writing 1 2 3 4 5, then the 1 2 3 4 5 is equal to 3 5 2 4 1, or it can be written as 5 3 2 4 1, like that also. So here the order of the term doesn't matter, and this set will be represented by this curly brackets. The elements of that set will be represented by curly bracket, and here the set should not have the duplicate elements. How we can specify a set? So while specifying a set, we need to consider certain things. To define a set, generally it is represented by a capital letter, and the elements of that particular set can be represented by the lowercase letters, like A, B, C, small cases, lowercase. And the best way, like see, there are two ways to represent that particular number, that particular set. One is list method, and that is the easiest way. So you enlist all the elements of that particular set, like A is equal to 1 2 3 4 5. This is the list method. You enlist all that elements. So this is the list method. If it is a large set, or if it is an infinite set, then this method will fail. Okay, so we have the another method. That method is called as the set builder, or this large numbers we can represent with the ellipsis, but again this ellipsis can be confusing. Okay, so we have the set builder method. Okay, set builder method, and the set builder method is basically, suppose I'm saying that there is a set D which is equal to x such that x is a prime and x is greater than 2. Okay, so it is the set of x such that x is a prime number and x is also greater than 2. So we can say that such a prime numbers which is greater than 2. Okay, or it can be the another cases, x is odd and x is greater than 2. So likewise, then we can say that there are certain cases also. So we can say that a set is said to contain the various members or elements that create that particular set, that make up the set. Okay, so here we can say that that element is member of, okay, member of or element of, or it belongs to that particular set is. And then what is the notation to represent that? So you can see that the notation is this one. So we can say that it's A belongs to S, or A is an element of S, or A is a member of S, like that. you can see that. And if it is not a member of that, then we can represent that with the A doesn't belong to S, or A is not a member of S. Okay, this is the example. Now, there are some generalized sets which we can utilize. So one of the set is natural numbers, set of natural numbers represented with capital N, set of integers represented by Z, set of positive integers, that is Z plus, Q, set of rational numbers where Q is represented at P by Q, set of P by Q such that P belongs to Z and Q belongs to Z, and Q is not equal to 0. Or there can be another set which is the standard one, R. R is a set of real numbers. So let's see the different types of the set. Here we have a universal set. Universal set is denoted by U, and it is a set of all the elements from which any given set can be drawn, or it can be called as a universal, which is like everything is in that one, every element is therein. So let's see two examples. So for this set is this one. We can say that the universal set can be the set of real numbers, and for this one we can say that it can be the set of real numbers, it can be set of the natural numbers, set of integers, or set of integers greater than equal to 0. Okay, multiple possibilities are there. Now, so set of student can be considered as the part of set of the students of the university. So we can say that if the student of a particular class I am considering, then this can be the part of that universal set, where universal set will be all the student in that university. Okay, so this type of examples can be there, and we are representing with the U letter. Okay, now to represent this particular set, okay, different set, and to understand that idea, Venn diagram can be used. What is Venn diagram? Venn diagram is a graphical representation. Okay, so the set can be represented in a graphical way. Here you can see two set, that is one is U and the other is S. U is a universal set, S is a set which is part of universal set. So the box is representing the universal set and circle is representing the any other set, set S. Okay, so here the set S, suppose if I am saying that set S is a set of all the vowels in the alphabet, and then universal set would be the set of all the alphabets. Okay, but see, remember one thing, that we are not mentioning that particular individual elements in the Venn diagram, only set is mentioned. Now understand the sets of sets. So by using a set concept, creating a set of set, so a set can contain other sets also. We can create the combination, like here 1 is also a set, 2 is a set, and 3 is also set, but is 1 2 3 is a part of set S. Likewise here 1 is a set, 2 is a set, but 2 is a set of another one, and then 3 is set of set, like that 3 times, and they are combinedly part of another set T. Likewise we have the multiple example. Okay, so if I am considering V, so V is having only 3 elements. Okay, one is this one, this and this last one. Take. So remember one thing, the individual element 1 cannot be said as equal to this set of 1, because here 1 is an element of that particular set. Here 1 is a standalone element. Again, this will be not equal to this one because this is a set of 1, like this. Okay, all of them are different. So that idea is there. Now let's see what do we mean by empty set. So an empty set is where the set is having 0 element, that is no element. So it will be called as an empty or null set, and this set will be represented by a phi symbol. Okay, that symbol. Now, so this null is equal to this empty part. So empty, writing the curly bracket without any element. We can utilize any of the notation. Okay, so an empty set is a set which can be the element of any other set, because it's empty basically, which I can say that it is a part of every other set. That is one idea. So I can say that this was original set, and in this empty set is a part. So this can be called as a valid set. Okay, so I can say that empty set is a part of every other set, but I cannot say that empty is equal to this, because for this set empty is a part of that set and it cannot be equal to a single element. Okay, so the first is a set of 0 elements and the second is set of at least 1 element. Okay, so wherever necessary we can replace this phi with the null set and that would be okay. Okay, so we can say that they are not equal in the cases. Now with the equal term, let's see what do we mean by set equality. Set equality is defined as if the two sets are equal if and only that if they have the same elements. So for example, if I'm having a set 1 2 3 4 5, okay, and the another is 5 4 3 2 1, just see that the elements are, whatever the elements are present in the first set is also present in the another set, then we can say that they are equal. Okay, here the order of the terms will not matter, order of the elements will not matter. Okay, and if it is repeated also, then also it will not matter, because still that particular set is a set, this is a set. So we can say that they are equal provided they have the same elements. Okay, so duplicate elements will not matter in this case, and if they are not having the same elements, then we can say that they are not equal. Okay, like this, here 5 is not there in the other set, so we can say that they are not equal. Now there is a concept of subset. Let's see what is subset. And suppose if I am having a set S, and if all the elements of S is also element of T, that is set T, then we can say that S is a subset of T. And how it is represented? Suppose if I am having S equal to 2 4 6 and T is 1 2 3 4 5 6 7, then S will be called as a subset of T, because 2 4 6 is also present in set T. So now we can say that the representation will be like this one. We are going to use this notation. S is a subset of T. Okay, so now if S is not a subset of T, then this can be written as this one. We can utilize this notation. Okay. So here in this below example, you can see that 8 is not present in the another one. So we can say that this particular set is not a subset of this because 8 is not present. Okay. So that is the case. Now we can say that any set is always a subset of itself, because if I am saying 2 4 6, then if I am considering another set S2 with a 2 4 6, so it is set of itself. So all the elements are present in the itself, so we can say that it is a subset of itself. Okay. Now, and that would be represented with this one, and this is valid. So equal set can also be considered. So I can say that empty set is always a subset of any other set, because already I have told you that particular part. So empty set is always subset of every other set. Empty set is always the part of every other set. Okay. So as well as I can say that every set is a subset of universal set, because every set will be a part of their universal set. Okay. So we can say that one. So, and how that can be represented? So we can read out this as for all the elements of X, if X belongs to A or X is a member of A, then X will belongs to this B. Okay. So if X is an element of A, then it implies that X is an element of B also. Now there is another type of set that is called as proper subset. Now we have studied that subset. Let's see proper subset. A set will be called as a proper subset if S is a subset of T, but S is not equal to T. Then it will be called as a proper subset. So suppose if I am having T as 0, 1, 2, 3, 4, 5, and my set S is 1, 2, 3, 4, 1, 2, 3 or 1, 2, 3, 4, whatever it is. But here you can see that S is having less elements than the T, like only some elements are matching, not all the elements. Okay, for S all the elements are there present, but I cannot say that S is equal to T. Then I can say that S is a subset, but it is not equal, and because of this I can say that S is a proper subset of T. You can see that here equality sign is not used. Okay, and so I'm using that one. Okay. So if it is a subset, this symbol subset with the equality sign can be used if it is a subset, and if it is not a equal but it is a subset, then it can be said that you can utilize the only subset symbol, proper subset. Okay. So equality is not there in the proper subset. So I can say that empty set is always a proper subset of every other set, but except itself. Okay, because it will be equal to that empty set. So I can say that empty set is proper subset of every other set, now how you represent this power that proper subsets in the Venn diagram? So this is the case. Here R is a set, S is a set, so this S is represented inside the R set. So this is the representation of Venn diagram. Now let's see what is the concept of set cardinality. So here the set cardinality relates with the number of elements of that particular set. So it can be written as this symbol, mod of A. Let's see the example. Suppose if I'm having set R, which is having 1, 2, 3, 4, 5 as an element, then I can say that the cardinality of set R is equal to 5. For a null set, the cardinality would be 0 because there is no element. Now suppose if I am having a set S which is represented at null comma every other set is also there. So but the cardinality would be 4 only. Okay. So this representation, this method is notation is used for vector length in the geometry also. Okay. So here if I am having a set with only one element, then that set will be called as the singleton set also. Okay. So let's see the another type of the set which is called as the power set. Now basically with the name you can say that it is something special. So here suppose if I am having a set S which is equal to 0 and 1, what will be the possible subsets of this particular set? How many subsets we can create? So with this one, as you know that particular null set is always subset of every other set. So null would be a part, and then since 0 is the element, so we can create a subset with a 0. Also we can create a subset with 1, as well as we can create a subset with both the elements. So the total number of elements will be 4. And how we know that particular total part, whether it is a correct one? Because since the cardinality of the original set is 2, then the cardinality of the power set would be 2 raised to this one. So that would be the case. Here the power set is represented at P of that particular set. So P of S, and the total element will be represented as this one. Okay. So now the cardinality of this power set would be taken as 2 raised to 2, that would be equal to 4. So you can say, you can define the formula. So here I am having a set T with a 0, 1, 2 element, then the total number of elements would be 8. Okay. So that is 2 raised to 3 equal to 8. Now power set of a null set is equal to the null set, that is set of null set, because null would be the part. Okay. See, this is not equal to null because here in the set one of the element is null. So here how you calculate the cardinality of the power set? With the 2 raised to n. If set, a single set is like a given set is having the n elements, then its power set would be having 2 raised to n elements. Okay. Let's see the concept of tuples. Tuples is basically the pairs which we are going to create, because this concept is required for the Cartesian product. So we are going to need this. So we are having the pair of x and y, which is going to specify a location like this one. Okay. Now, so for a 3-dimensional representation, 1, 2, 3, 4 will not mean as 3, 2, 1, because it's a combination of 3 values. So in an n-dimensional, that will be called as n tuple. So for 3-dimensional it will be 3 tuple, and 2-dimensional a pair, that a group of the 2 likewise. Okay. So that is the case. So basically these tuples are always ordered one. Ordered. The order will be fixed. We cannot change that. So for a set, order was not important. But here in the tuple, the order is very important. Like it is a ordered one, fixed order is there. Okay. So suppose I want to learn about the concept of Cartesian product. So a Cartesian product is a set of all ordered two tuples. So let's see. So here the Cartesian product will be denoted as A cross B, and here we are going to use parenthesis to represent the Cartesian product. We are not going to use the curly brackets. Okay. And for a two-dimensional Cartesian product, we can say that it will be ordered pairs of Z cross Z. Here Z is an integer one. Okay. And it would be in a 2D space. For example, you have a set A with elements A and B and set B as elements 0 and 1. So how you create this particular Cartesian product? So the Cartesian product of A cross B can be given as A comma 0, that is A comma 0, then A comma 1, sequence wise, then B comma 0, B comma 1, and you create a set of all these elements, all these tuples. So that would be called as the total Cartesian product. So this Cartesian product is the formal definition of this Cartesian product can be called as this one, that is A cross B can be specified as A comma B. It will be set of A comma B such that A is a member of set A and B is a member of set B. Both the conditions should be true. It should belong to both the parts. Okay. So this general case, all the possible grades in the class will be Cartesian product of set S of all the students in the class and the set G of all the possible grades. So both should be common. So here, suppose if I'm having this set S with the students and G as a class, then you can create the Cartesian product of that one as this one, and the final grades will be with this one, like it will be with a subset of this Cartesian product, because Cartesian product is a all possibility. Okay, it is set of all the possible grades. So my final grades will always be a subset of this one. Okay, so we can utilize this concept while studying the relation. Okay, now we can extend this concept of Cartesian product on more than two sets. Like this idea can be extended to a three-dimensional coordinate, and which will create the Cartesian product in three-dimensional space. Okay, so that's it for part 1. We will continue this topic in the next part, where we will learn about the various operations performed by this one. Okay, so thank you very much. Please join us on YouTube, like and share, subscribe to this channel. Thank you very much.